Imagine discovering that one of the most influential scientists in human history is someone we know almost nothing about. No confirmed portrait, no reliable record of his parents, no surviving biography written during his lifetime, not even a certain date of birth. And yet, for more than 2,000 years, his ideas have shaped mathematics, engineering, architecture, astronomy, physics, education, and the way human beings define what it means for something to be proven true. His name was Euclid, and the strange thing about Euclid is that he may not have invented most of the mathematics associated with his name. His real achievement was something even more powerful. He gathered scattered mathematical knowledge, organized it into a logical system, and showed generations of people how to build complicated truths from a small number of simple assumptions. The result was a book called The Elements. For centuries, it became one of the most influential books ever written. But before we understand why, we have to travel back to a world where mathematics was changing from a collection of practical tricks into something much more ambitious. More than 2,000 years ago, the ancient Mediterranean was filled with merchants, sailors, architects, engineers, philosophers, and astronomers. They needed mathematics for very practical reasons. Farmers needed to measure land. Builders needed angles. Astronomers needed geometry to understand the sky. Merchants needed arithmetic. Surveyors needed methods for calculating distances and areas. But mathematics was also becoming something deeper. Greek thinkers were asking a new kind of question. Not simply, does this method work? But why must it work? That difference sounds small. It wasn't. It changed the intellectual history of humanity. Earlier civilizations, especially in Egypt and Mesopotamia, had developed sophisticated mathematical techniques centuries before Euclid. They could solve problems involving areas, volumes, ratios, equations, and astronomical calculations. But Greek mathematicians increasingly emphasized deductive proof. A mathematical statement was not enough. You needed to demonstrate why it had to be true. And that idea was already developing long before Euclid appeared. Pythagoras and his followers explored numbers and geometry. Plato regarded mathematical reasoning as a path toward deeper knowledge. Eudoxus developed powerful ideas about proportion and magnitude. Theodosius and other mathematicians contributed to geometry and astronomy. Euclid entered this intellectual world at exactly the right moment. And yet, almost everything personal about him remains uncertain. We do not know exactly when he was born. Most historians place his active period around the beginning of the 3rd century BCE. We know he was associated with Alexandria in Egypt, probably during the reign of Ptolemy I, whose rule began in 305 BCE. Alexandria was one of the great intellectual centers of the ancient world. It had been founded only a few decades earlier by Alexander the Great. After Alexander's death, his empire fragmented. Egypt came under the control of Ptolemy and his dynasty. The Ptolemies transformed Alexandria into a major center of learning. Scholars gathered there. Books were collected. Mathematicians, physicians, philosophers, astronomers, poets, and other intellectuals worked in an environment designed to preserve and expand knowledge. The famous Library of Alexandria became a symbol of that ambition. And somewhere within this world, Euclid taught mathematics. But this is where the historical record becomes frustratingly thin. We do not have a detailed account of his childhood. We cannot confidently name his parents. We do not know whether he grew up in Alexandria. We do not even know exactly where he was educated. Later sources suggest connections with the mathematical tradition associated with Plato's Academy, but the details are uncertain. So if someone tells you a detailed story about Euclid's childhood, be careful. Much of it is probably reconstruction rather than documented history. What we can say with much greater confidence is that Euclid inherited a mathematical tradition that was already extremely rich. And instead of simply adding another isolated discovery, he did something extraordinary. He tried to organize the whole subject. That would become his masterpiece. But getting there required a completely different way of thinking. Imagine being handed hundreds of mathematical results. Some are about triangles. Some are about circles. Some are about ratios. Some are about numbers. Some were discovered by different mathematicians at different times using different approaches. Now imagine being asked to turn all of that into one coherent system. You cannot simply make a list. You have to decide what comes first. Which statements should be treated as basic? Which can be proven from those basic statements? And how do you make sure every step actually follows from the one before it? This was the challenge. And Euclid's response was the elements. The title can be misleading. It sounds like a beginner's textbook. It wasn't. The Elements was a vast mathematical synthesis. It contained 13 books covering geometry, arithmetic, ratios, number theory, and solid geometry. And although Euclid's name became attached to the entire work, historians generally understand that he was not creating everything from nothing. He was compiling, organizing, refining, and presenting earlier mathematical knowledge. In other words, Euclid was not necessarily the person who discovered every theorem in the Elements. He was the architect of the system, and that distinction matters, because the most revolutionary part of Euclid's work was not one particular theorem. It was the structure. Start with a small foundation, then prove everything else. Think about building a massive structure. You could pile stones randomly until you had a wall. Or you could begin with a foundation, establish a framework, and make sure every part connects to the structure underneath it. Euclid chose the second approach. At the beginning of the Elements, he defined basic objects: a point, a line, a surface, an angle, a circle. Some of these definitions are famous. A point is described as something with no parts. A line is described as breadthless length. These definitions are not modern scientific definitions in the way we would define an object in physics. They are starting concepts. Euclid then introduced assumptions. Some were called postulates. Others were common notions. The idea was simple. If you agree to a small set of basic assumptions, you can use logical reasoning to establish more complicated results. One of the most famous assumptions concerns parallel lines. In simplified form, Euclid's fifth postulate says that if a line crosses two other lines and the interior angles on one side add up to less than two right angles, then the two lines will eventually meet on that side. Compared with the first four postulates, it is complicated. And mathematicians noticed this. For centuries, they wondered whether the fifth postulate was actually necessary. Could it be proven from the others? That question would eventually lead to one of the greatest revolutions in mathematics. But Euclid's original system was built around the geometry of ordinary experience. A straight line, a circle, a triangle, a rectangle, a point, simple objects. From these, the Elements built an astonishing mathematical universe. One of the first things Euclid established is that certain constructions can be performed using only a straightedge and compass. For example, you can construct an equilateral triangle. Start with 2 points. Draw a circle centered on the first point. Draw another circle centered on the second. Where the circles intersect, you have a third point. Connect the 3 points. You have an equilateral triangle. It sounds elementary now, but the deeper lesson is important. Euclid wasn't just telling you the answer. He was showing you a procedure whose correctness could be justified. This distinction between calculation and proof became central to the mathematical tradition that followed. And then comes one of the most famous results in all of mathematics, the Pythagorean theorem. For a right triangle, the square of the longest side equals the sum of the squares of the other two sides. If the shorter sides have lengths 3 and 4, the longest side has length 5. 3 squared is 9. 4 squared is 16. 9 plus 16 is 25. And the square root of 25 is 5. Most people learn the formula, but Euclid's treatment belongs to a deeper tradition. The point is not merely that the numbers work. The relationship is universally true for every right triangle, and a proof explains why. Euclid's proof uses areas. Squares are constructed on the sides of the triangle. Then the areas are related through geometric reasoning. The theorem becomes more than a useful formula. It becomes a consequence of the structure of geometry itself. This is one of the central powers of proof. A calculation tells you what happened in one case, A proof tells you why it must happen in every case covered by the assumptions. And Euclid pushed this method much further. The Elements also contains some of the foundations of number theory. This is the mathematics of whole numbers and their relationships. One of Euclid's most famous algorithms appears in Book 7. Today we call it the Euclidean algorithm. Its purpose is to find the greatest common divisor of two numbers. That sounds technical, but the basic idea is surprisingly simple. Suppose you want to find the largest number that divides both 48 and 18 evenly. Start with 48. Subtract 18 twice. That leaves 12. Then compare 18 and 12. Subtract 12 from 18. That leaves 6. Now 12 divides by 6 exactly. So 6 is the greatest common divisor. The modern algorithm uses division rather than repeated subtraction, making it much faster. But the fundamental idea goes back to Euclid, and it is still used today in computer science, in cryptography, in algorithms, in number theory. Something written more than 2,000 years ago still operates inside modern mathematical systems. But Euclid's number theory contains something even more famous: the proof that there are infinitely many prime numbers. Prime numbers are numbers greater than 1 that can only be divided evenly by 1 and themselves. 2 is prime, 3 is prime, 5 is prime, 7 is prime, 11, 13, 17, and so on. At first, it might seem possible that the primes eventually run out. Maybe there is some final prime number, unimaginably large, after which no new primes exist. Euclid showed why that cannot happen. Imagine, he argues, that you have a complete list of every prime number. Multiply all of them together, then add 1. The new number cannot be evenly divided by any prime from your original list, because dividing it by any one of those primes leaves a remainder of 1. So either the new number itself is prime, or it has prime factors that weren't on your list. Either way, your supposed complete list was incomplete. There must always be another prime, and another, and another. It is a beautifully simple argument. No giant calculation is necessary. No computer is needed. Just logic. And that is Euclid's great gift: the ability to turn an apparently complicated question into a small, decisive argument. But the Elements did not stop with triangles and numbers. It moved into ratios, proportions, circles, areas, three-dimensional shapes, polyhedra. By the final books, Euclid was dealing with the geometry of solid objects. The Elements culminates in the construction of the 5 regular polyhedra. These are three-dimensional shapes whose faces are identical regular polygons and whose vertices have the same arrangement. The tetrahedron has 4 triangular faces. The cube has 6 square faces. The octahedron has 8 triangular faces. The dodecahedron has 12 pentagonal faces. And the icosahedron has 20 triangular faces. These 5 shapes became known as the Platonic solids. Euclid's treatment helped preserve and organize the mathematical understanding of these remarkable objects. And this is where the Elements reveals its true scale. It wasn't just a book about measuring land. It was an attempt to build a complete logical world. But there was a problem hiding inside that world. A problem so deep that it would occupy mathematicians for nearly 2,000 years. The fifth postulate: parallel lines. For centuries, mathematicians tried to prove that the fifth postulate was actually a consequence of the other assumptions. If they could, the system would be simpler. But every attempt failed. And eventually, something astonishing happened. Mathematicians discovered that they didn't have to prove the fifth postulate. They could reject it. And if they changed it, they could construct entirely different geometries. In one kind of geometry, sometimes called hyperbolic geometry, there can be multiple lines through a point that never meet a given line. In another, spherical geometry, the familiar rules of flat geometry change in different ways. On the surface of a sphere, for example, what looks like a straight path can behave very differently from a line on a flat sheet of paper. This discovery transformed mathematics. It showed that Euclidean geometry was not the only logically consistent description of space. It was one possible geometry, and that realization eventually became essential to modern physics. More than 2,000 years after Euclid, Albert Einstein's theory of general relativity would describe gravity through the geometry of spacetime. The geometry of the universe at large scales is not simply the flat geometry people encounter on a sheet of paper. Euclid did not predict Einstein. He did not know about curved spacetime. He could not have imagined modern physics. But his framework created a language and a tradition in which questions about the fundamental geometry of reality could eventually be asked with extraordinary precision. That is one of the strangest features of intellectual history. A question that begins with a line and a triangle can eventually lead to questions about the universe. And yet, despite this enormous influence, Euclid himself remains strangely invisible. We know his work far better than we know the man. That is unusual. For famous scientists, we often have letters, portraits, family histories, personal rivalries, stories about childhood. Euclid gives us almost none of that. The earliest important surviving biographical information comes from later writers. One of the most important sources is Proclus, a philosopher and mathematician who lived roughly 700 years after Euclid. Proclus wrote a history of geometry in which he discussed Euclid and placed him in the mathematical tradition of Alexandria. But Proclus was writing long after Euclid's lifetime, so his information has to be treated carefully. This is why historians cannot confidently reconstruct Euclid's personal life. Even his exact birthplace is uncertain. Some later traditions connect him with places outside Egypt, but there is no secure evidence establishing where he was born. His family is also unknown. His marital status is unknown. Whether he had children is unknown. What did Euclid look like? Unknown. The famous images of Euclid that appear in textbooks and museums are later artistic representations, not authenticated portraits. So if you see a picture of an elderly man with a beard, holding a compass, you are not looking at a verified photograph of Euclid. You are looking at an imagined face attached to a historical name. There is another problem. The name Euclid itself became so famous that later traditions sometimes attach stories to him that may not be historically reliable. One famous anecdote claims that King Ptolemy I asked whether there was an easier way to learn geometry than studying the elements. Euclid supposedly replied that there is no royal road to geometry. It is a memorable line. It captures the spirit of mathematical discipline perfectly. But historians cannot confidently establish that the conversation actually happened. It belongs to the tradition surrounding Euclid, not to securely documented biography. The same caution applies to another story in which a student asks what practical benefit geometry will provide, and Euclid allegedly orders someone to give the student a small payment. Again, it is a clever story, but clever stories are not the same thing as evidence. And perhaps that uncertainty tells us something important about Euclid. His personality disappeared. His system survived. We don't know whether he was charismatic or quiet. We don't know whether he enjoyed teaching. We don't know whether he was impatient with students. We don't know what his private ambitions were. We don't know whether he understood how influential his work would become. All we really have is the mathematics. And that mathematics is revealing in its own way. The Elements is remarkably systematic. It suggests a mind deeply concerned with order. But there is an important historical correction to the popular image of Euclid. He should not be imagined as a lone genius who suddenly invented geometry from scratch. That is almost certainly wrong. Mathematics had been developing for centuries before him. Egyptian mathematicians had practical geometry. Babylonian mathematicians had sophisticated numerical methods. Greek mathematicians before Euclid had already proved many geometric results. The Pythagorean theorem existed in mathematical traditions before Euclid. The theory of proportions was already highly developed. The study of regular solids had earlier roots. So what did Euclid contribute? Organization, selection, logical architecture, and perhaps most importantly, preservation. Some earlier mathematical works have been lost. We know about certain mathematicians partly because later authors mention them. Euclid's Elements became a vessel through which much older mathematics survived. It is like finding an ancient library that has been carefully reorganized into one enormous logical structure. And this structure proved incredibly durable. For centuries, Copies of the elements circulated in Greek and later in Arabic. During the medieval period, Islamic scholars studied, translated, commented on, and expanded the mathematical traditions associated with Greek works. Arabic mathematical scholarship played a major role in preserving and transmitting Greek mathematical knowledge. Eventually, the elements entered Latin Europe through translation traditions that connected the Islamic world, Byzantium, and Western Europe. When printing technology arrived in Europe, Euclid became one of the major mathematical works to be printed. Its influence spread even further. For generations of students, studying geometry meant studying Euclid. In many educational traditions, geometry was taught as a sequence of definitions, propositions, and proofs. Students were trained not simply to calculate. They were trained to demonstrate, and that habit changed the way educated people thought about certainty. The influence reached far beyond mathematics classrooms. Architects used geometry, surveyors used geometry, astronomers used geometry, engineers used geometric reasoning, artists used perspective and proportion, cartographers relied on geometric principles. Navigation depended on mathematical relationships. And as science became increasingly mathematical, the habit of constructing knowledge from clearly stated assumptions became one of the defining ideals of scientific reasoning. Of course, modern science is not simply Euclidean geometry. Science depends on observation, experiment, measurement, statistics, models, and evidence. But the mathematical ideal of deduction remains fundamental. If a model begins with certain assumptions, and if the logic is correct, then its consequences follow. That idea is everywhere. In physics, in engineering, in computer science, in economics, in cryptography, in formal logic. Even in software, mathematical reasoning can help determine whether a system behaves as intended. And here is the remarkable part. The Elements has survived not because every statement in it describes the physical universe perfectly. Modern mathematics has moved far beyond Euclid. Instead, it survived because the method is so powerful. Start with definitions. State assumptions. Prove consequences. Check every step. Repeat. That method can be applied to entirely new mathematical worlds. But Euclid's influence was not always positive in every context. For centuries, the authority of the Elements became so great that some people treated Euclidean geometry almost as if it were a perfect description of physical reality. Then came the 19th century. Mathematicians such as Nikolai Lobachevsky, János Bolyai, and Carl Friedrich Gauss explored the possibility that Euclid's parallel postulate might not be necessary. Bernhard Riemann later developed another profound form of geometry. The result was a mathematical revolution. Space itself could be studied in different ways. Geometry no longer had to mean one single system, and this eventually opened the door to modern geometry and mathematical physics. So the greatest legacy of Euclid may contain a paradox. He created one of the most influential geometric systems in history, and his system eventually helped mathematicians discover that it was not the only possible one. That is not a failure. It is a sign of how mathematics grows. A powerful framework teaches us what questions to ask. Then, eventually, its unanswered questions lead us somewhere new. But there is another misconception worth clearing up. Euclid's Elements is not exactly the same thing as Euclid's discoveries. The work is a compilation and synthesis. Some propositions likely originated with earlier mathematicians. Euclid may have modified proofs. He may have rearranged material. He may have selected which results belonged in the overall structure. Some portions may reflect contributions from different earlier sources. Modern scholars continue to debate the precise history of individual propositions. So perhaps the best way to understand Euclid is not as a man who stood alone in a room and invented mathematics. Imagine instead a vast intellectual river. Egyptian mathematics flows into it. Babylonian traditions flow into it. Pythagorean ideas flow into it. Platonic mathematics, the work of Eudoxus, the geometry of earlier Greek thinkers. And then Euclid builds a remarkable channel through which much of that knowledge can flow into the future. That is a different kind of genius. not necessarily the genius of discovering one spectacular new fact, but the genius of seeing how thousands of pieces fit together. And that kind of achievement is easy to underestimate, because when a system works perfectly, the system itself can become invisible. Every time a student proves that the angles of a triangle have a certain relationship, they are entering a tradition that stretches back more than 2,000 years. Every time someone uses the Euclidean algorithm to find a greatest common divisor, they are using an idea with ancient roots. Every time a mathematician proves a theorem from a set of axioms, they are participating in the same broad intellectual culture that Euclid helped define. And every time an engineer, physicist, architect, or programmer asks, what follows if these assumptions are true? They are practicing a form of reasoning that Euclid's work helped make central to mathematical thought. But what happened to Euclid himself? Here again, the historical record becomes almost completely silent. We do not know the exact year of his death. We do not have a reliable account of his final days. We do not know where he was buried. There is no famous deathbed statement that historians can confidently authenticate. No final letter. No personal diary. No detailed memoir. The man disappears into history. The book does not. And that may be the most fitting ending for Euclid, because his work was never primarily about himself. The Elements deliberately pushes the individual mathematician into the background. The proof matters more than the personality. The reasoning matters more than the reputation. A theorem is not true because Euclid said it was true. It is true because the argument establishes it. That is a radically powerful idea. It means mathematical knowledge can outlive the person who discovered or organized it. A student thousands of years later does not need to trust Euclid personally. They can examine the reasoning. They can follow the steps. They can challenge the assumptions. They can find an error if one exists. And that is part of why mathematics has such extraordinary longevity. Ideas can become independent of their creators. Euclid's name survived because his arguments could be tested by people who never met him. His culture disappeared. His political world disappeared. The language in which he wrote became a historical language. The institutions around him changed. Empires rose and fell. Libraries burned. Manuscripts were copied and recopied. And still the geometry remained. Think about that for a moment. A man who lived more than 2,000 years ago left behind no verified portrait and almost no personal history. Yet his mathematical fingerprints are everywhere. In classrooms, in textbooks, in engineering drawings, in computer algorithms, in theories of space, in the language of proof, and perhaps most importantly, in the expectation that a claim should not become true simply because an authority says it is true. It should be demonstrated. That expectation reaches far beyond geometry. It is one of the foundations of rational inquiry. But there is one final twist. Euclid's geometry describes an idealized world. Perfect points, perfect lines, perfect circles, objects that do not physically exist in exactly that form. No physical ruler is infinitely thin. No real circle is perfectly exact. No material surface is perfectly flat. And yet these ideal objects allow us to reason about the real world with astonishing precision. This reveals another profound idea. Mathematics does not have to be physically perfect to be practically powerful. A perfect circle may not exist in nature, but engineers can use circular models to design machines. Architects can use geometric models to construct buildings. Scientists can use mathematical abstractions to describe physical systems. The power comes from abstraction. We remove the messy details. We keep the relationships that matter. Then we reason about the simplified system. Euclid mastered that kind of abstraction more than 2,000 years ago. And today we live inside a world built from abstractions. Digital images are represented as numbers. Computer programs operate through formal rules. Modern encryption depends on mathematical structures. Satellites calculate positions using geometry and physics. Robots navigate using mathematical models. Buildings are designed through geometric calculations. And spacecraft travel through environments described by equations. The world around us may look physical, But underneath much of modern civilization is a mathematical skeleton. Euclid helped teach humanity how to see that skeleton. His story is therefore not really the story of one man discovering geometry. It is the story of a civilization learning to demand reasons. A triangle is not merely a shape. It is a system of relationships. A number is not merely a symbol, can have a structure. A theorem is not merely an opinion, can be derived. And knowledge itself does not have to depend entirely on authority, can be built, step by step, statement by statement, proof by proof. That is why the Elements became so influential. It was not simply a book of answers. It was a demonstration of how to construct certainty from foundations. And perhaps that is why Euclid remains relevant even now. Not because every geometric assumption he used is the final truth about space. We know it isn't. Not because he invented every theorem attributed to him. He didn't. And not because we know his life story. We barely do. Euclid matters because he helped establish a way of thinking that proved far larger than the man himself. Start with what you know. Make your assumptions explicit. Question what seems obvious. Follow the logic. And if the conclusion survives every step, then you have something stronger than intuition. You have a proof. More than 2,000 years have passed since Euclid worked in the intellectual world of ancient Alexandria. The buildings have changed. The languages have changed. The instruments have changed. The technology surrounding us would be almost unimaginable to him. But draw a triangle on a piece of paper today. Pick up a compass. Measure an angle. Ask whether a statement must be true. And suddenly you are standing in the same intellectual tradition. That may be Euclid's greatest legacy. Not a statue, not a portrait, not even a book, but a habit of mind. The habit of asking, how do you know? And once humanity learned to ask that question with mathematical precision, there was no going back. So the next time you see a simple triangle, a circle, or a straight line, remember what is hiding inside those ordinary shapes. A revolution in human thought, a system assembled from assumptions, a tradition that survived empires, languages, wars, and centuries, and a mathematician whose life is almost completely lost to history, while his ideas remain alive in the world around us. Perhaps that is the ultimate mystery of Euclid. We may never know exactly who he was, but we can still follow his reasoning. And maybe that is the most powerful form of immortality a thinker can have. Not to have your face remembered, but to have your questions continue to shape the minds of people who will never know your name. And perhaps the most Euclidean question we can ask ourselves today is the simplest one of all. When we believe something is true, do we believe it because someone told us, or because we have taken the time to prove it?